Scientists just gave robots living muscles that can feel their own strength. Source: July 2026, Biohybrid Robotics Research. If you like my videos, subscribe my channel, and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. For a discussion, write down your views in comments. For more than a century, every robot humanity has ever built has shared one fundamental limitation. Whether it was a factory robot assembling automobiles, a humanoid robot walking across a laboratory floor, or a robotic arm exploring deep space, every movement relied on rigid mechanical parts. Electric motors rotated gears. Hydraulic pistons pushed metal joints. Pneumatic systems compressed air to generate force. Although these machines became faster, stronger, and increasingly intelligent, their method of movement remained surprisingly primitive compared to the natural world. Biological organisms solved the problem of motion hundreds of millions of years ago using an entirely different strategy. Instead of relying on rotating gears or hydraulic pressure, living creatures move through contracting muscle fibers, soft, flexible tissues capable of producing enormous strength while constantly sensing their own condition. Muscles can adjust force almost instantly, repair microscopic damage after strenuous activity, and perform delicate movements requiring incredible precision. Engineers have long admired this elegant biological solution, but reproducing it inside a machine seemed nearly impossible. Now, a remarkable breakthrough announced in July 2026 may have changed that. Researchers have successfully integrated laboratory-grown skeletal muscle directly into robotic systems, creating biohybrid machines capable not only of moving with living tissue, but also of sensing how much force those muscles are producing. For the first time, robots may be beginning to move less like machines and more like living organisms. If you like my videos, subscribe to my channel and press the bell icon to turn notifications on so you never miss the latest breakthroughs in science and technology. And don't forget to like and share this video with your friends and colleagues. Your comments are always welcome and help create great scientific discussions. To appreciate why this achievement is so important, we first need to understand the problem engineers have struggled with for decades. Traditional robots are incredibly powerful, but they are also incredibly rigid. Their movements are generated by electric motors connected through metal gears, belts, or hydraulic actuators. Every motion must be carefully calculated and controlled because the machine itself has almost no natural flexibility. If a robot accidentally pushes too hard against an object, it can easily crush it. If something unexpected blocks its movement, enormous forces may damage both the robot and its surroundings. Human muscles behave very differently. They naturally compress, stretch, and adapt as conditions change. Every movement continuously adjusts itself using information flowing from specialized sensory structures embedded inside the muscles and tendons. Even before your brain consciously notices it, your muscles already know how much force they're generating, how quickly they're stretching, and whether they're approaching their physical limits. This built-in feedback allows biological movement to remain both incredibly powerful and extraordinarily gentle at the same time. Replicating that natural intelligence has remained one of robotics' greatest engineering challenges. Rather than trying to imitate muscles using increasingly sophisticated electric motors, researchers have now taken an entirely different approach. Instead of copying biology, they are beginning to use biology itself. Scientists grow living skeletal muscle tissue inside laboratory environments using carefully controlled nutrient solutions, growth factors, and stem cell technologies. Once mature, these muscle fibers are transferred onto specially engineered polymer frameworks that serve as a robot's artificial skeleton. Unlike conventional robotic joints where motors and gears remain separate mechanical components, the living muscle bonds directly to the flexible structure. The result is a seamless connection between organic tissue and synthetic materials. As the muscle contracts, it pulls naturally against the polymer skeleton exactly as muscles pull against bones inside the human body. This creates movement that is fluid, silent, and remarkably lifelike, eliminating much of the stiffness traditionally associated with robotic systems. Building such a system requires extraordinary precision. Engineers first create the robot's flexible skeletal structure using advanced 3D printing techniques capable of producing microscopic attachment points that encourage living cells to anchor themselves securely. Next, muscle precursor cells are deposited layer by layer through a specialized process known as 3D bioprinting. Over time, these cells mature into aligned muscle fibers that grow directly along the framework's engineered surfaces. Unlike ordinary printing, which simply deposits plastic or metal, bioprinting constructs living tissue capable of continuing to develop after fabrication. Nutrient-rich growth media keep the cells alive, while biochemical signals encourage them to organize into functional muscle bundles. Eventually, the artificial skeleton and living tissue become so closely integrated that distinguishing where biology ends and engineering begins becomes increasingly difficult. Of course, growing muscle is only part of the challenge. Muscles do not contract automatically. Inside every animal, movement begins when the nervous system sends tiny electrical signals through motor neurons. These electrical impulses trigger chemical reactions inside muscle cells, causing microscopic protein filaments to slide past one another and generate force. Researchers recreate this biological process electronically. Carefully timed electrical stimulation pulses are delivered directly into the engineered muscle tissue, mimicking the signals normally produced by the nervous system. By precisely controlling the timing, frequency, and strength of these pulses, scientists can generate extremely accurate contractions measured down to fractions of a millimeter. The muscles respond almost exactly as they would inside a living organism. Instead of spinning a motor shaft, the robot contracts actual living muscle, allowing smooth acceleration, gentle stopping, and continuous adjustment of force throughout every movement. Perhaps even more impressive is the discovery that these living muscles retain one of biology's greatest advantages, the ability to heal themselves. Every time we exercise, tiny microscopic tears develop throughout our muscle fibers. Rather than weakening us permanently, these small injuries trigger natural repair processes that rebuild the tissue stronger than before. Laboratory-grown muscle exhibits remarkably similar behavior. During repeated operation, microscopic damage inevitably accumulates within the biohybrid limbs. But provided nutrients and proper environmental conditions remain available, the living cells begin repairing this damage on their own. Proteins reorganize, damaged fibers regenerate, and structural integrity gradually returns without engineers, replacing worn mechanical components. Conventional robotic actuators slowly wear out until they eventually fail completely. Biohybrid muscles may instead recover continuously throughout their operational lifetime, potentially extending reliability far beyond traditional machines. The advantages become even more dramatic when researchers compare energy efficiency. Hydraulic actuators generate enormous forces, but maintaining hydraulic pressure requires powerful pumps that consume significant electrical energy. Electric motors are more efficient than hydraulics, but still waste considerable power overcoming friction, heat generation, and mechanical resistance. Living muscle operates using an entirely different energy strategy. Refined through hundreds of millions of years of biological evolution, muscle fibers convert chemical energy into mechanical work with remarkable efficiency while storing elastic energy naturally within tendons and connective tissue. Preliminary experiments suggest that biohybrid grippers consume only a fraction of the energy required by comparable hydraulic systems while producing similar levels of precision. That increased efficiency could dramatically extend battery life in future mobile robots, reducing charging frequency while enabling longer autonomous operation in environments where replacing batteries is difficult or impossible. The precision these muscles provide is equally extraordinary. Most industrial robots rely on complex pressure sensors, force sensors, and sophisticated software algorithms simply to determine how firmly they are gripping an object. Even then, handling extremely delicate materials remains challenging. Living muscles behave differently. Because biological tissue naturally compresses and continuously senses its own contraction force, biohybrid robotic grippers can gently manipulate incredibly fragile objects almost instinctively. Researchers have demonstrated movements delicate enough to handle soft fruit without bruising it, and biological samples as sensitive as individual living cells without requiring large arrays of external pressure sensors. The muscle itself effectively becomes both the actuator and the sensor simultaneously, greatly simplifying robotic control while dramatically improving dexterity. Another remarkable advantage comes from muscle's natural elasticity. Traditional robotic systems often require separate mechanisms for speed and precision. Fast movement typically sacrifices accuracy, while precise positioning demands slower operation. Biological muscles perform both seamlessly. Elastic fibers absorb sudden forces, smooth rapid accelerations, and stabilize fine movements automatically. A single muscle can produce explosive motion one moment and delicate, perfectly steady positioning the next. This natural adaptability allows biohybrid robots to transition smoothly between lifting heavy objects, manipulating fragile materials, or performing complex repetitive tasks without requiring entirely different mechanical systems. These capabilities are opening exciting possibilities across medicine. One of the most promising applications involves soft surgical robots capable of navigating the human body with unprecedented safety. Conventional surgical instruments remain relatively rigid even when miniaturized. Biohybrid robotic devices, powered by living muscles, could gently navigate narrow arteries, blood vessels, or delicate internal tissues while generating almost no damaging friction. Because their movements closely resemble natural biological motion, these devices may perform minimally invasive procedures with greater precision while reducing trauma to surrounding tissues. Future surgeons could potentially guide living robotic instruments through parts of the body that are currently inaccessible using existing technologies. The same principles could completely transform prosthetic limbs. Today's advanced prosthetics already incorporate sophisticated electronics and artificial intelligence, yet many users still describe their movement as mechanical rather than natural. Biohybrid actuators offer the possibility of prosthetic limbs that respond with the smoothness, speed, and flexibility of genuine biological muscles. Because living tissue naturally adjusts force continuously, future prosthetic hands may grip objects as effortlessly as human hands, while artificial legs could walk, run, and maintain balance with far greater comfort and stability than existing mechanical systems. Researchers are also imagining entirely new forms of aerial robotics inspired directly by nature. Instead of noisy electric propellers spinning thousands of times per minute, future environmental monitoring drones could flap lightweight muscle-powered wings similar to birds or insects. Such systems, would move almost silently through forests, wetlands, and other sensitive ecosystems, allowing scientists to observe wildlife without disturbing natural behavior. The extraordinary energy efficiency of muscle-powered flight could also increase endurance while reducing environmental impact, opening opportunities for ecological monitoring impossible with today's conventional drones. Despite these remarkable advances, significant challenges remain before biohybrid robots become widespread. Living muscle requires continuous care. Unlike electric motors, biological tissue needs oxygen, nutrients, stable temperatures, and carefully regulated chemical conditions to remain healthy. Researchers are actively developing miniature nutrient delivery systems capable of sustaining muscle outside controlled laboratory environments. Designing compact methods to circulate nutrients while removing metabolic waste remains one of the largest engineering obstacles facing the field. Without solving this problem, living robotic systems will remain limited to carefully maintained research environments rather than operating independently in the real world. Scientists are optimistic that these challenges can be overcome during the coming decade. By around 2030, researchers hope to move beyond isolated muscle fibers toward fully integrated biological control systems incorporating synthetic nerves, artificial blood vessels, and engineered vascular networks capable of nourishing living tissues continuously. Instead of stimulating muscles using external electrodes alone, future robots may contain artificial neural circuits capable of coordinating movement, much like biological nervous systems. Such developments would represent an enormous leap from today's simple biohybrid actuators toward machines, whose internal organization increasingly resembles living organisms. That future raises profound philosophical questions. Throughout history, machines have been built from metal, plastic, and electronics, while living organisms have been composed of cells, tissues, and biological chemistry. Biohybrid robotics is beginning to dissolve that distinction. When a robot moves using living muscle, repairs its own microscopic injuries, senses its own strength through biological feedback, and perhaps one day contains synthetic nerves and vascular systems, where exactly do we draw the boundary between a machine and a living organism? Does intelligence alone define life? Or does life begin when biology itself becomes an essential part of the machine? For now, these remarkable creations remain firmly under human control. They are tools, carefully engineered for scientific discovery and practical applications. But history has repeatedly shown that technological revolutions often begin with seemingly modest laboratory demonstrations before reshaping entire industries. The first transistor looked insignificant. Early integrated circuits contained only a handful of components. The earliest artificial intelligence systems solved only narrow problems, yet each represented the beginning of technologies that transformed civilization. Biohybrid robotics may now be reaching a similar turning point. By combining the precision of engineering with the extraordinary capabilities of living tissue, scientists are creating machines that no longer simply imitate biology, they are beginning to become biological themselves. And that may fundamentally redefine what we mean when we call something